Yes, sir, I can hear you.
Okay, just a second. So first one, let's start off with alkanes. Okay, so now we're basically going to write reactions. So let's start off with alkanes. And we're going to cover. We're going to take a deeper dive on some of the reactions, but we'll do that later. So, alkanes were saturated hydrocarbons. Which means everything is single bonds. And so this is one example of what an alkane looks like. It's got, the molecule name would be propane in this case. There are 3 carbon atoms, and that's propane. So that's it. Physical properties quickly. It's a non-polar molecule. So it's a non-polar molecule, and therefore it's only going to have one type of force, which is van der Waals forces, which are basically instantaneous dipole. So that's instantaneous dipole induced dipole. So 2 molecules would only have that force, and since it's a non-polar molecule, van der Waals forces, they increase with size. So the main conclusion is that it increases with size. So bigger molecules are going to have more van der Waals forces. So bigger molecules have increase of size. Bigger molecules have higher melting in. They have higher melting and boiling points. So that's one thing, and not soluble in water because of that. So not soluble in polar solvents like water, because it's not going to attract it. Like water. So that's pretty much it, and you should know that melting and boiling points would increase, so bigger molecules would either be liquids or solids. Let's try and cover the reactions quickly. So what are some of the reactions for alkanes? So reactions for alkanes are number 1, there's a reaction that is known as free radical substitution. That's the proper name for the reaction, free radical substitution, and it's previously known as, you've already studied that earlier as well. So it's previously known as chlorination or bromination. So it's known as chlorination or bromination. This specific reaction, you have to go into a lot of detail about this reaction, but not right now. I'm going to go into the mechanisms of the reactions right at the end. We'll just cover what the reaction is. The reaction is simple. The reaction is that you've got an alkane. Let's say you've got a 3 carbon atom. alkane or any number of, and it's going to react with either chlorine or bromine. So it's Cl2 plus ultraviolet light. Or you could also have bromination as well, or Br2 plus UV light. So what will happen is that the hydrogens are going to get substituted by Cl or Br, and it could be any number of them. Like you can get all sorts of molecules. There could be one Cl that might get substituted at any position. Or you could have 2-3 hydrogens getting substituted, or all of them as well. Or you could have all of them getting substituted as well. So maybe you have this molecule and all of them, they get substituted. Depending on how much chlorine and how much ultraviolet light you've got. So maybe all of them get substituted and you get Cl everywhere. So you get Cl everywhere. So that is free radical substitution, and the other byproduct of the reaction is an HCl molecule. That is produced. So is the reaction clear? What the reaction is?
Sir, can it occur with the alkenes also, free radical substitution?
Yeah, I'm going to come to that. It can happen with anything that has a carbon chain. Okay, I'll just have to add it right now. That free radical substitution is possible with any alkyl carbon chain. So it occurs with all alkyl chains. And so for example, if you have a carboxylic acid, then the alkyl chain kind of looks like an alkane. I mean, if you ignore one end, the rest of the molecule is very similar to an alkane. So this part over here is kind of the same as an alkane. So free radical substitution would be possible, and one of the hydrogens over here can get substituted as well. Let me one second. So somewhere over here, the Cls might get substituted randomly. I mean, maybe all of them, maybe some of them, and completely random. There's no specific position at which the Cl would like to go or attach itself. Is that part clear?
Yes,
Yes,
sir.
sir.
So that's another. And one more thing about this is that you might also get products which have multiple number of carbon atoms. But we'll discuss that. We'll discuss that later. Okay. Right now, I'm not going to discuss mechanisms of the reaction. That's the overall reaction. That's the overall reaction. And you've got chlorine or bromine getting substituted into the carbon chain. That's one of them. And that's probably the only reaction. I'm going to discuss crude oil distillation and cracking separately, not with alkanes. So that's the main one for alkanes. Remember, combustion is the reaction that happens for every organic compound. We're going to talk about that later as well. So that's alkanes. So we're done with alkanes. But this one, remember, I'm just putting a star over here. So I'm putting a star over here. We're going to do the mechanism of the reaction, how this reaction happens in a lot more detail. Let's move towards alkenes now. So alkenes are your unsaturated. So they are your unsaturated hydrocarbons. So these are your unsaturated hydrocarbons. Water alkenes, they've got a double bond. Basically, unsaturated hydrocarbon means that they've got a double bond somewhere. And what type of reactions would an alkene? The first thing is the property. Properties are similar to alkanes, no difference. Same physical properties as alkanes. So you can just copy paste what you just wrote before. These are also non-polar. These are also, they also have van der Waals forces. More importantly, let's talk about reactions. And their significance. The first reaction is number one. These are known as electrophilic addition reactions. Again, not going into details, what is electrophilic addition? We don't know right now. We'll discuss that later separately. So electrophilic addition is the name of the reaction. In O-levels, you learned addition reactions. This is specifically electrophilic addition. And what happens, number one? Number one is known as bromination. Now in bromination, you've got an alkene and it's got a double bond H. And you've got a Br2 molecule. So the molecule just literally gets added. The conditions are room temperature, and the conditions are you either use aqueous or inert solvent. An example of an inert solvent is carbon tetrachloride, CCl4. So the molecule remains exactly the same. Bromines get added to the double bonds. It's the double bond part that is reactive. So everything happens onto the double bond. The double bond breaks, turns into a single bond, and two Brs get added. On both carbon atoms. Is that clear?
Yes, sir.
Yeah.
So let's do another example. If I have a molecule and now I'm drawing a skeletal formula of a molecule. And it's got double bonds. There's a double bond here and there's a double bond at this point. So let's say this is my molecule and I'm brominating it. And you can also do chlorination with this. Just 1 second. So the product would be, nothing should happen to the molecule. It's just these carbon atoms where the bromines are going to get added, these two and these two. The double bonds would go away and one Br is going to get added to, so one of the Br will get added to this carbon atom and one Br will get added to this carbon atom. There's going to be a Br that's going to be added to this carbon atom and one Br getting added to this carbon atom. I did it on the wrong one, just a second. So anyways, that's going to be my product. Let me put BRs over there. Here's that's how the reaction would look like. So that's how the reaction would look like if you do the same thing on the skeletal formula. Just remember double bonds, these two carbon atoms, that's where the BRs are going to get added. Yes, Hamza.
Sir, would there be like any sort of observation for when the reaction would be completed?
Yes, I mean, this is a very important reaction. What is it used for?
To make halogenalkenes?
See, I mean, it is making a halogenoalkane, so that point is correct. But
I'm sorry, but is it to test for unsaturated compounds?
so this reaction is basically a test for unsaturated hydrocarbons. So it's a test for figuring out whether it has alkenes or not. So that's the significance or the importance of this reaction. So it's a test for identification of alkenes of unsaturated hydrocarbons. So anything that has double bonds, they're going to be tested this way. And what is the observation? What will happen when bromine reacts?
Orange to colorless?
So it's the red, brown, or orange. I mean, all these words are used: red, brown, orange. Br2 is decolorized. Is decolorized. So that's the significance of the reaction, right? Is that clear? And also remember, this one would also happen with Cl2. Usually Cl2 is not used, but same thing with Cl2. So a similar reaction would happen with Cl2. Now the second one. Is this clear? The first one, is this clear, everyone?
Yes, sir.
It's no different. You've studied this in O-levels as well. Next one is known as hydrogenation. So hydrogenation is what? Hydrogenation is it's reaction with H2. So you kind of have the same reaction. So I'll just copy everything. It's kind of going to be going to be similar, except it's going to be with hydrogen now. So instead of Br2, you'll just have, the only difference would be you'll just have H2. That's about it. So you can just repeat everything. The conditions would be different. You will have H2 gas And it's not going to be at RTP, it's going to be at 150 to 200 degrees centigrade. And there's going to be a catalyst. It's going to be a nickel or a platinum catalyst that's going to be used. And instead of Br getting added, you'll have hydrogens that would get added. So that's it, exactly the same reaction. And instead of forming a halogenoalkane, it's actually forming an alkane. So what happens is that your unsaturated molecule turns into a saturated molecule.
Sir,
Yes.
for the one above, how is it different to the bromination with an alkane?
Which one?
For the one above, yeah.
Yeah, this one.
Like, how is it to test for alkenes if alkanes do the same thing as well?
The difference is the alkanes do that with UV light.
Okay.
And so it's RTP, and preferably you should write absence of light. This should happen this will happen in the dark. Is that clear?
Yeah.
So, so this reaction can't happen in the light?
It will happen in the light, but in the light, free radical substitution will also happen. Like the hydrogens will get, instead of addition, there's going to be substitution that would also happen. Like the bromines will, like over here, the hydrogens might randomly get substituted by bromines as well. So it will not just be happening at this point, but it also be happening at the other points as well. Is that clear?
Yes, sir.
As anyways, what's the significance of hydrogenation? What does it do?
Make it unsaturated.
But where industrially, where is it used?
Maybe
Acidifies,
because
I mean, you use it industrially to make margarine, unsaturated vegetable oils are converted into margarine. So you turn it into margarine. So if you have an unsaturated vegetable oils are like complicated molecules. If I can just if we have molecule, just a second. So that's, this one is like an unsaturated vegetable oil. So what will happen is, if I just copy this over here. So that's like an unsaturated vegetable oil. This is one big molecule, and you see double bonds over here at different points, carbon, double bond, carbon. So if you hydrogenate it, all the double bonds would go away. Is that clear? And hydrogens are going to get added to it. And it will turn into margarine. Is that point clear?
Yes, sir.
Yes, sir.
So the question is, why do you even do that? Like, why don't you use why hydrogenate an unsaturated vegetable oil? Why can't you just have unsaturated vegetable oil? Why do you want to convert it into margarine? That's one question. The answer to that one is because vegetable oils are liquids and they have low boiling points, right? Most of the vegetable oils like sunflower, olive oil, canola oil, etc. They have relatively low boiling points, right? And they are liquids. What is margarine? Margarine has slightly higher boiling points. and it's in the form, it's a solid, it's got higher boiling points, and it's a solid. I mean, although it melts very quickly, but it is a solid. There's not much much of a big difference between the two, but there's a slight difference. This one is liquid, this one is. So if you want to, like, if you want to spread on your want to spread something on your toast, margarine is a much better option. I mean, you can't do that with vegetable oil. So that's an industrial way of making something that is very similar to butter. Is that clear?
Yes, sir.
I said, so why does adding hydrogen make it a higher boiling point? What's the reason behind that? Like what happens? Adding hydrogen, what does it do? It makes the molecule bigger, right?
Yes.
So if you have a bigger molecule, what type of forces would increase? Right. So it makes a bigger molecule, which is why you'll have more van der Waals forces. So you'll have more van der Waals forces, which is why margarine kind of has a slightly higher boiling point, right? Is that clear, everyone?
Yes, sir.
And we can just quickly copy this one as well. Like if you hydrogenate this molecule over here, it's exactly the same. It's just hydrogens getting added. That's it. So instead of the BRs, you'll have, remember the position, it's the double bonded carbon atoms. That's where all the addition is taking place. So hydrogens are getting added to these carbon atoms. Anyways, next one is hydration. The third one. So number 3, that is hydration. And that's a reaction with water. And that's no difference, no different. It's pretty much the same thing, except, so I'll just copy the same reaction. And this time we'll have water getting added. That's about it. And that would result in the formation of alcohols. So this one is, you got an alkene and unsaturated, I mean, forget unsaturated. It turns into an alcohol. What will happen now is the conditions are definitely going to be different. You'll have water in the form of steam because you use a higher temperature for this. The reaction happens at 300 degrees centigrade temperature and 60 atmosphere pressure. And you've got 60 atmosphere pressure, and you've got an acid catalyst, phosphoric acid. Which is your catalyst. And you can also use, you can use H2SO4. Usually it's avoided because it's a good oxidizing agent. H2SO4 can also be used. Yes, Hamza.
Sir, isn't this reaction reversible?
Not this one.
Okay.
I mean, I'm pretty sure this is not a reversible reaction because the conditions are so extreme. I'm not sure. I mean, it's not going to. I mean, yes, it's. I mean, what do you mean by reversible? Because reversible means that it happens or reverses at the same time, which it doesn't. I mean, you can convert an alcohol back to an alkene. That is possible, but it's a separate reaction. Is that clear?
Yeah. Okay. Got it.
Okay, so I mean, when you use the term reversible, that means it's going to reverse at the same time, which it won't. As anyways, you've got an alcohol forming. Now there's an issue. There's a problem with this one, and that is that this molecule, the one that I've drawn, I've added an H and OH, right? This molecule is propan 1-ol. It's an alcohol that is produced and it's propane 1-ol. There's going to be another version of the molecule as well. Because what will happen is that the H and the OH can bond the other way around. Like they're going to bond to the double bonded carbon atoms, but what can happen is that the OH could bond on the left one and the H could bond on the right one. So you're going to get two different products, and these are basically two different products because the OH position is different. Over there it was on the right carbon atom. Over here it's in the middle carbon atom. So this one is propane. This one is propane 2-ol. Right? Is that clear?
Yes.
And then there's another issue, and that issue is that you're going to have major and minor products. Why you're going to have, that's a separate discussion. We'll do that right at the end. This one is going to be your major product. And that one over here is going to be your minor product. Remember, major and minor products would only matter if you are getting two different molecules. So if you're getting two different molecules, if there's a possibility of getting two different molecules, like over here, you didn't have a possibility of getting two different molecules because if the hydrogens are getting added, it doesn't matter if this hydrogen gets added to this one. You switch the position, it's still the same thing. So you're not getting two different products. Major and minor products would be an issue if you have an unsymmetric alkene. It's not going to be an issue for symmetric alkenes as well. Like if I had an alkene, and remember, this is only an issue for unsymmetric alkenes. Hopefully everyone knows what an unsymmetric alkene is. So this is an unsymmetric alkene. Wouldn't be an issue if I had, let's say, ethene. If I had ethene, it doesn't matter where the H or where the OH gets added, right? Because I'm not going to get two different products. Like if I draw the products, the double bond would go away. The H will get added to one carbon atom and the OH will get added to the other carbon atom, right? Even if I reverse it, if I make it the other way around, it's still the same thing, right? Is that clear? So unsymmetric alkenes, that's not an issue. Sorry, symmetric alkenes, it's just going to give you a single product. Let me just write that down as well. So symmetric alkenes, so this is the only product. Unsymmetric alkenes, you're going to get two different products. Is the idea clear why you're getting two different products? Is this clear?
Yes, sir.
Yeah.
So the next question is, what do you mean by major and minor product? Major product is the one that you're going to get more of it. Like if there are 10 molecules produced during the reaction, then there would be 9 of them would be this one, and there's going to be one which is this one. So how do you select which one is the major product, which one is like, how did I figure out this one is the major product and this one is the minor product? So what you do is there's a rule for that. The explanation would come a lot later. Why is there a rule? Why does this rule work? We'll talk about that much later. The rule is known as the Markovny. So it's known as the Markovnikov's rule. What the rule suggests is that when you have an issue where you're getting two different products during an addition reaction, the major product is the one where the H likes to get added to the carbon in. So it likes to get added to the carbon in serial bond O that is already bonded to more H atoms. So that is already bonded to
But sir, then shouldn't the major product be
Achha, so he already bonded to more H atoms directly. So let's focus on this.
So both of them are like bonded to the same number.
Nahi,
wouldn't,
how many H atoms are bonded to this one?
But right now three, but like before the hydrogen got
Yeah.
added, weren't they two only?
There were two, right? So this one was
Yeah.
bonded to two. How many H atoms is this bonded to? Like
one?
ignore. There's only one, right?
No, two.
No, there's.
Oh, okay, never mind, never mind.
I mean
Yeah,
that those H's are with this carbon
that
atom,
was the carbon.
right?
Yeah, okay.
So is that clear that I mean you look at this molecule actually.
But what about the one down?
Which one?
No, the one right of it.
If I say this, I'm just let me add this over here. So this is bonded to two hydrogens and this one is bonded to just one hydrogen, right? So two and this is bonded. So anyways, this is bonded to one. So the H will bond with the carbon that's already bonded to more H atoms. So if you have a water molecule, H and OH are going to get bonded. So the H is more likely to be bonded to the carbon that's already bonded to more H atoms. So you're talking about this one, right? Kiss per question that this one?
G, sir, yeah.
No, over here it doesn't really matter. Like it's. I told you that in symmetric alkenes, that's not an issue because you're only going to get one product.
All right, sir.
Like even if I switch the positions, it's exactly the same thing.
Okay.
So you don't have an issue with that one. So remember the Markovnikov's rule. You don't know what the reason is behind that. We'll discuss the reason right at the end. But this is the Markovnikov's rule. The next, yes.
Is there a rule like the OH will add to the carbon that has more alkyl groups?
I mean, that's the exact opposite of the. I mean, that's the same rule.
Oh, okay, it's the same thing.
Yeah.
Yeah.
Because every time it is going to be an H, so it's a lot easier because every time there's not going to be an OH. I mean, you can generalize this rule a lot easier. So it's a lot easier to remember.
Okay.
Now the fourth one. Let's finish this. The fourth one is. So the fourth one is. What's the fourth one? So the number 4. It's hydrogen halides. So no specific reaction specifically for hydrogen halides, I mean conditions. Like if I have, I mean everything is the same, so I'll just copy that. Again, you're going to have major and minor products. So hydrogen halides are basically HCl, HBr, HI, etc. So if I have a reaction with, let's say, HCl, so I mean the conditions are kind of irrelevant. Usually they happen at RTP, or maybe some sort of heating is required. So let's say I have a reaction with HCl. What will happen is instead of H and OH, it's going to be H and Cl that are going to get added. So it's going to be HCl, or Cl would be over here, right? And this is 1 chloropropane and 2 chloropropane. And the other one is 2 chloro. Two chloropropane. So you have a major product, you've got a minor product in the same way. Is this clear? Yes, Hamza.
Our teacher told us about this rule in a different way. He said that the major product would be the second degree of the product or
Nee, I've-
second degree of the.
What I'm right now doing is I'm making things a lot easier at the moment. It's just that you don't have to go into second degree or anything to identify the major products. It's a lot easier to identify the major product by just that the H will get bonded to the carbon that's bonded to more H atoms. We're going to do the reasoning later. Is that clear?
Okay.
Okay,
So
it's,
this rule, Markov's, it's the same thing.
it's the same thing. Because that is the explanation for the rule. We'll come to the explanation later. We'll keep things simple first, so that it's easier to remember things, because most of the time they're not going to look for the explanation. They're just going to talk about what's the major product, what is happening, TK in this reaction. So we're doing that part first. And then once we are done with the reactions, once we know what the reactions are, then we're going to talk about like what's the issue with the Markovnikov's rule? Why do we have a Markovnikov's rule in the first place? What's the reason behind that? So we're going to learn the reasoning behind that. We're going to learn the reasoning about bromination. Where's bromination? I mean, we're going to talk about this in detail. We're going to talk about electrophilic addition, like why does the reaction happen? What does electrophilic addition mean? Is that clear?
Okay, sir.
And we'll do that for because you don't have to learn the reasoning for a lot of reactions. There's just 4 or 5 reactions for which you have to sort of dive deeper into them and learn the mechanisms. So we'll talk about Markovnikov's rule as well. We'll talk about the other stuff as well. But at the moment, it's a lot better. Just remember, H will get added to the carbon that's already bonded to more H atoms. That's it. Okay. So that's all about alkenes. Tomorrow we'll try and cover the reactions of we'll try and cover all the reactions for alcohols. There's one left, which is we're going to do redox together. I'm not going to touch redox as well. I'm going to group all of the redox reactions together. There's addition polymerization that's left. For alkenes, we'll probably do that tomorrow, and we'll probably cover the reactions for alcohols as well. Okay.
Okay, sir. Inshallah.
So let's continue tomorrow.
Okay.
No, sir, Allah Hafiz.
Allah Hafiz.
Allah Hafiz.
So,